Hello everyone and welcome to a new course, Magnetic Circuits. So before we start the course, we need to ask ourselves a question. Have we ever wondered how electrical energy is transferred so efficiently from one circuit to another without direct electrical connection? So if we look around any modern power systems, power plants, substations, electric vehicles, renewable energy systems, or even our laptop chargers, one component quietly plays a crucial role in all of them: the transformer. So how devices like transformer power our homes, industries, and electronics so reliably? So the heart of every transformer or any electrical machine is a fundamental concept that engineers must understand. So the answer of this question lies in magnetic circuits. So we need to cover this concept before we expose ourselves to the transformer. So what is the contents? We first need to explore the physics and engineering behind the magnetic circuits. So in this course, we will start from the basics by understanding electric and magnetic fields, and then see how the magnetic circuit is formed and analyzed. We will also explore the analogy between electric and magnetic circuits, cover the magnetization characteristics of magnetic materials, and understand concepts like self-inductance, AC sinusoidal excitation, and losses in magnetic cores. Finally, we will discuss the mutual inductance, which is the key principle that makes transformer possible. So by the end of this course, we will have a strong foundation in magnetic circuit that will naturally lead us to understanding the single-phase transformer and their operation in real power systems. As usual, our course will have plenty of numerical examples. So let's start. What is a field? We are not going to cover Maxwell equations in this course. That one will be a course by its own. So we are going to have a simple definition for the field: spatial distribution of a scalar or vector quantity, which may or may not be a function of time. So a field can only be detected by its effect: electric field, force on an electric charge; magnetic field, the presence of current due to a movable charge. I'm going to focus on magnetic field. Sources of magnetic field: in power frequency range, something like 50 Hz or 60 Hz, also 400 Hz up to 800 Hz for aerospace applications. Sources may be related to an equivalent current flow. So for example, if we have current carrying conductor, if we have a certain number of turns N and carry a current I, so there will be a flux lines as we can see here. Also, if we have a permanent magnet, so we have a north pole and south pole, so we have the flux lines. So magnetic field is directional. Field lines emanate from a north pole and enters a south pole. So that one is going to generate a north pole and south pole as well. Each line or flux forms a closed loop, and lines of magnetic flux can never cross or intersect. As we know, if an electric current flowed in a conductor, a magnetic field is produced. So we are going to use the right-hand screw rule to determine the direction of a magnetic field around a current-carrying conductor, as shown in the figure. So for example, if we have current into the paper or into the screen, so the field will be clockwise as we can see here. So these are the field lines. But if the current is out of the paper or out of the screen, so the field will be anti-clockwise. So in this video, we covered an introduction about the magnetic circuits and why we need the magnetic circuits, and we started looking for the magnetic field, how to form the magnetic field. And if we have a current carrying conductor or a permanent magnet, we can have a flux lines based on the direction of the current. So what will I watch in video number 2? In video number 2, we are going to cover what is the magnetic circuit itself. See you in the next video. Thank you.